Hello everyone. We are starting a new chapter, chapter 28, and this will be the first chapter on magnetism. So we will be taking a break from the circuits material. We will revisit a little bit of the circuitry when we get to the end of chapter 30, but for now we need to start talking about the magnetic effects that are associated with electric charge. And usually when you hear about electricity or magnetism, the two topics are kept separate from one another, even though they're really two sides of the same coin. Where you have one, you're going to have the other, but which one you see the effects from has everything to do with how the system is set up, how the geometry of your system is set up. Basically, from what point of view are you looking at this system, that determines what kind of effects that you're going to see. So in certain systems, you will see electric effects. In certain systems, you'll see magnetic effects. In some systems, you may see both. And so now we need to talk about what these magnetic effects are going to be. And at some point in our youth, we've probably played with a magnet. And one of the more basic types of magnets that are out there is what's called a bar magnet. And these bars will have the letters N and S printed on them typically. And these stand for north and south poles. So magnets are polar, just like the electric dipole was polar. And that's because we had two distinct ends on the electric dipole. And our electric dipole would have electric field lines, which would be given off based on the charge value of either end. We know that the positive charges will have their field lines pointing out. The negative charges will have their field lines pointing in. But then as our charges start getting closer and closer to each other, we will see those field lines start to bend. Well, it's a very similar picture with magnets. And we're going to see our magnetic field lines. Oops, I wanted to use a different color for that. We're going to see our magnetic field lines being produced in pretty much the same picture. I'll try to keep these symmetric here. Well, we've spent a good month or so trying to figure out what the electric fields are in a given system based on how the electric charges are distributed. And we had the Gauss's law approach, we had the calculus approach. And depending on how symmetric the system was, Gauss's law was pretty good at helping us figure out what the electric field for a system was. But now we have to figure out what is the magnetic field going to be. Now I've got this rough drawing here, but a drawing can be a bit deceptive, especially since this is a freehand drawing. I would much prefer to have some kind of a mathematical expression that describes the magnetic field. Now, our electric field, we've been using capital E, and it is a vector, so we have the vector hat over the top. For the magnetic field, it might make sense to use a capital M, but that might get confused with the mass of an object. There are some other terms that M can be used for. We'd rather use a letter that hasn't been used yet to denote our magnetic field. And so for that, we're going to use capital B. And just like the electric field, the magnetic field is also going to be a vector. It has a direction that it points in, as is denoted by the direction that these field lines are pointing. For magnets, we will see the field lines point away from the north end and towards the south end. So very, very similar to what's happening with the plus and minus charges. Well, if electric fields are produced by electric charges, does that mean that there's some kind of a corresponding magnetic charge? And the idea is kind of nice, except there is no monomagnetic charge. And when I say mono, what I mean is for single. With electric charges, we can have a single charge value that is either positive or negative, or in the case of a neutral charge, it could be null. But so far, there is no such thing as a monopole magnet. In other words, we can't produce a magnet just by having a north or a south end. Every magnet, regardless of how large or small, is going to have a north and a south end. And so this idea of magnetic charge doesn't quite work in our case. Just to give you a better example, if we were to take our bar magnet and cut it in half, what would we have? Would we have just a north half and a south half? Well, no. We would just have two smaller bar magnets. And the line in which we cut this thing in half, the opposite end of the top north would now be a south, and the opposite end of the bottom south would be a north. And so we just have two smaller magnets. And because we've cut the magnet in half, not only have we produced two smaller magnets, but these two smaller magnets are going to be weaker in the effects that they produce individually. Well, then we can try cutting those in half, and we would make four smaller magnets, each with a north and a south end. But the question would be, how many times can you cut this in half and still get a dipole relationship? Well, you can keep doing that until you get down to a single atom. And we're gonna talk about how a single atom can act as a magnet. But regardless of the size of the magnet, we are always going to have a north and a south end associated with that magnet. So instead of trying to define some kind of a magnetic charge, what we're going to do is we're just going to stick with the idea of electric charge, and we'll see how these electric charges influence the outcome of how a magnet is made and how that magnet is going to behave. Where we need to start with our discussion is at the beginning. We're basically going to go back to chapter 21 and reproduce almost everything that we've seen for the electric cases, but for the magnetic scenario. And one of the first things that we had back in chapters 21 and 22 was this relationship between electric force, electric charge, and electric field. We know that if we place an electric charge in some kind of external electric field, there will be an electric force that acts on it. And the ratio of the electric force to the charge was what gave us the electric field. So is it possible to take that idea and apply it to the magnetic system? In other words, is there some kind of magnetic force out there that will relate to an electric charge and a magnetic field? And here I've put this will be an approximation or a proportionality if you want, because I'm not quite sure if this is exactly equal or not. Well, if we go term for term with our force and charge and field, then the ratio of magnetic force to electric charge, is that going to be equal to the magnetic field that we're looking for? And unfortunately, the answer is no. This is not equal. There is one missing quantity. And that missing quantity is the speed or velocity of the electric charge. In all of our previous chapters, when we discussed the electric field that was being produced by charges, we always had these charges sort of fixed in place. We might have had a charged sphere, and that sphere had its charge uniformly distributed about the surface. And because that charge was uniformly distributed, that charge was pretty much static. It wasn't going to move. But now we have to consider the fact that we can have charges moving, especially when it comes to things like wires. Because the moment that we connect a wire to some kind of potential source, like a battery, or as we started calling it in the previous chapter, an EMF, this is going to allow those charges to start moving through the system. And it's not until these charges start to move that we actually notice any of these magnetic effects. And so the one extra term that is missing from this expression up here is the velocity of the charge. And so we're going to have to include the velocity of the charge. And actually, I kind of got ahead of myself here. I don't want to incorporate the vector hats with this just yet. And that's because velocity is also a vector. But I don't know about you, I don't remember ever dividing by a vector. I've only ever divided by the magnitude of a vector. But that's okay, because we can now take this expression and we can rearrange it to say that the magnetic force that acts on a moving charge of velocity v through field B. We can put those vector hats together, but I now have the product of two vectors. And when it comes to vector multiplication, there are two possibilities. You can have the scalar dot product, or you can have the vector cross product. And the words out front are there to remind us what the outcome is going to be of each of these products. For the dot product, you are going to produce a scalar quantity. For a cross product, you are going to produce a vector quantity. Well, that's what's happening here. I have two vectors, velocity and field, along with a scalar, which is the charge, and that's producing a third vector quantity, force. And the only way that I can do that is, well, has to be a cross product. And vector cross products can be evaluated by taking the magnitude of each vector times the sine of the angle that exists between them. Now, over here, A, B, C, D, these are just random letters that I used for the vector notation. Should have the vector hats on there as well. But up here, B is the magnetic field, and so one way that we can evaluate this cross product is to take the magnitude of each vector multiplied together with the value of the charge times the sine of the angle that exists between the two vectors. So V and B. And that will tell me the magnitude of the magnetic force that is acting on that charge. Now, the velocity was the missing piece to this expression. If we just took the same expression from the electric case and we didn't include the velocity, well, our answer for the magnetic field would be off by that scalar value of whatever the speed was, which is why we had to incorporate it in here. But there's another consequence of taking a cross product, and that is that the resulting vector of your cross product has to point in a direction that is perpendicular to the original vectors that were used in the product. In other words, this vector D that was produced by the cross product of vectors A and B, D has to be perpendicular to vector A, and D has to be perpendicular to vector B. So how does that happen? Well, it's really only going to happen in a three-dimensional system. If I draw two vectors on this screen, maybe this is vector A and this is vector B, the cross product of these two vectors is going to produce a third vector that has to be perpendicular to both of these. Now, the only way that we're going to make a vector that is perpendicular to both of these is if that vector either points into the screen or out of the screen. That's the only way that I can get these two vectors to be perpendicular to their resultant. And so how do I draw 3D vectors on a 2D surface? Drawing 3D on a 2D surface is not that easy, but we don't want to try. We kind of want to stay away from trying to draw 3D on a 2D surface if we can avoid it at all. In this case, we have the standard XYZ reference frame, and you kind of have to use your imagination and apply a little bit of depth perception there to envision this 3D reference frame. But if we can get away without having to pretend so much, all the better. So how do we label a vector that's pointing into the board or out of the board so that we know and recognize it, and that everybody else who's looking at our work knows and recognizes it? Well, remember that vectors are arrows. If you had an arrow that you shot out of the page, in other words, this arrow is coming at you, it's coming right at your eye. what part of the arrow do you see? Well, you see the tip of the arrow. So there's the tip of the arrow, and it's coming right at you. Well, if I put that on my page, how is someone else supposed to know that that's a vector? How am I supposed to know that that's a vector? How am I supposed to know that that's not, just a little mark that I accidentally made on the page? Well, I have to bring a little bit of attention to that mark, and so I'll draw a circle around it. And a circle with a dot in the middle indicates a vector out of the page or out of the board. What if you fired the arrow into the page? So what if you fired the arrow away from you? What would you see? Well, in that case, you would see the fletching or the feathers on the back end of the arrow. And so it would look something like this. But again, we need to specify that this is a vector and not just an X. We don't want somebody to read this and think that it's a variable X or a multiplication symbol that just went astray somewhere. So we will also put a circle around that. And that will indicate to us and everyone else that looks at our work that this is a vector that is going into the page. Well, which one is it? When I take the cross product of these two vectors, do I make a vector that goes into the page or out of the page? And that'll be a discussion for a little bit later when we actually have some example problems to do. So we'll hold off on that for right now, but this is some notation that we're going to need, and we're going to be using it quite a bit in our future discussions. So that's why we have that out there right now. The next thing that we have to consider is how we're going to evaluate this stuff. Let's take a basic problem of a charge of 20 microcoulombs traveling with a velocity of, let's say, 1,000 meters per second. So pretty fast, pretty small particle. And we'll place that into a magnetic field of magnitude 0.5, and now would be a good time to discuss the units of magnetic field. Let's take the expression that we have right here. We can put the units together by combining the units of all the other terms that we have over there. Force is in newtons, charge is in coulombs, and then we have velocity in meters per second. That ratio will get flipped. We have Newton seconds over Coulomb meters. And we're going to shorthand that to a Tesla, or T for short. So Tesla is the units for magnetic field. We have our three terms. So let's find out what is the magnitude of the magnetic force that is going to act on this charge. QV cross B. We can evaluate this by taking the magnitude of each vector times the sine of the angle that exists between them. Well, I guess we need to know what direction these vectors are pointing in. Except I'm going to give us quite a few different options. Our charge of 20 microcoulombs, I will, in every situation, have that charge moving to the right. But I will have that charge moving through magnetic fields of different orientations. And so the first magnetic field that this charge moves through will be pointed in the same direction as what the charge is traveling. So these two vectors are running parallel to each other. In the second case, we will insert our charge into a magnetic field that is pointing to the left. Then we'll take the charge and we'll insert that into a magnetic field that is pointing up. Then we'll take the charge and we'll insert it into a field that's pointing down. Then we'll take our charge. We will insert it into a magnetic field that is pointing into the board. So the X with the circle in it implies a vector that is pointing away from us. Don't get that mixed up with your charge. And then we'll have our charge move through a field that is pointing out of the board. So what we have here with these 6 different combinations is every conceivable combination that you can have between a velocity vector and a magnetic field vector. Now, obviously, there are going to be plenty of other angles that we can set up between two vectors. In fact, there's infinite combinations, but all of those other combinations are just going to be a combination of one of these 6 possibilities. Now, I don't have to consider velocities going in other directions, and that's because the only thing that I need to compare right now is this angle relationship. If I were to change the direction of the velocity vector, then I would really just be shuffling between the different orientations for field, and I would get the same outcomes in general. All right, so now we want to know in what direction will the magnetic force vector point. For these first 2 examples, that should be pretty straightforward, because if we try to evaluate this system, and I have 2 vectors that are running parallel to each other, well, parallel vectors have an angle of 0, and sine of 0 is 0. So I would get 0 force. Shift this up just a little bit. I would get 0 force. I would have no magnetic force acting on that charge as it moves through that orientation of magnetic field. Likewise, I would not get any magnetic force acting on this charge. Even though we flip the magnetic field over, the angle relationship between those vectors is now 180 degrees. Sine of 180 degrees is also 0. But everything else that I have, the remaining 4 combinations, all of these have a 90-degree relationship between the velocity vector and the magnetic field vector. Well, for this first combination here, I have velocity pointing to the right. I have magnetic field pointing up. So the only options that are left in terms of the direction that the magnetic field can point have to be either into the board or out of the board, because our magnetic field vector has to be perpendicular to the original 2 vectors that were used to produce it. And the only way I can do that is to have that force vector point either into the board or out of the board. But how do we know which is which? We can't just flip a coin. With the next example, we have our velocity pointing to the right, and we have our magnetic field pointing down. Again, I would have to have my force pointing either into the board or out of the board, but which is which? And if I flip the magnetic field vector over, does that mean that the resulting force is going to flip over as well? Well, I'm still at kind of a 50-50 chance here in guessing the direction that my magnetic force needs to point. So if you don't mind, I'll just go ahead and tell you the direction that the magnetic force is going to point, and then we'll talk about how we evaluate that outcome. We'll go ahead and list out these combinations here. So for combination number 3, the resulting direction of the magnetic force is going to be out of the board. For case 4, the resulting magnetic field will be into the board. Now, again, we'll talk about how I'm getting these answers in a moment. For case 5, we have our velocity pointing to the right. We have our magnetic field pointing into the page. The resulting magnetic force will point up. And lastly, case 6, we have our magnetic field pointing to the right, or excuse me, we have our velocity pointing to the right, we have our magnetic field pointing out of the page towards us. The resulting magnetic force will have to point down. So you're thinking to yourself, how is he getting these values? What is he doing? Is there a trick? And the answer is yes. And that trick is called the right-hand rule. In a previous lecture, we defined the X, Y, Z axes. I'm going to try to draw this. Again, trying to draw 3D on a 2D surface is not the easiest thing. But when it comes to drawing an XYZ axis, there is a proper way to do that. In most cases, people would just randomly assign XYZ to whatever direction that they want, but there is a correct way of doing it, and this is it. At least in terms of the right-hand rule, which is what we're going to use through the remainder of this course. There are other rules. In case you're wondering, yes, there is a left-hand rule, but I am not going to teach it because if I do, that's just going to confuse people. And I already see enough students sitting down at an exam struggling with this. I see a lot of people who are right-handed, writing with their pencil or their pen with their right hand, and then they try to use the right-hand rule with their free hand, which is their left hand, and they get their answers wrong. So if you're a left-handed person and you write with your left hand, this is your day, because you can continue writing and use the right-hand rule at the same time, because you'll have your right hand free. So this right-hand reference frame, the Y and the Z axes are the axes that are lying on the page itself. And the X axis is the axis that is coming out towards us. So I guess we could draw the x-axis as a circle with a dot in it, but in some cases it's just easier to see the reference frame drawn like this. And so what we're going to do is we're going to take this reference frame and we're going to reproduce it using our right hand. And so I'm going to have to try to draw this. Go back to this color here. That's not going to work. Come on, give me the eraser. There we go. Try it like this. All right, so I realize this doesn't look very much like a hand, but what we have right here and here and here, this is the index finger. So index for X. The middle finger goes this way. And this is going to be your y-axis. And then this is going to be your thumb, which will be your z-axis. Now, what I have down here, these are just the two leftover fingers. So this is your ring finger and your pinky finger, and I'm just going to curl those in underneath because we're not going to use them as part of the right hand rule. So maybe it'd be better if I just didn't have those in there. But our index finger, our middle finger, and our thumb, those will be the directions that we use to point in any of the given directions. And so this is how we will define the right hand rule. Now, you can rotate your hand in any direction that you want, but the relationship between the x-axis, the y-axis, and the z-axis as it pertains to your hand is always the same. No matter how you rotate your hand, your index finger will always be the x-axis, your middle finger will always be the y-axis, your thumb will always be the z-axis. So that's the first part about the right hand rule. The second part about the right hand rule is how we will evaluate. We have these different vectors that are pointing in all different directions. But when it comes to all of the different pairings here, there's really only 3 different choices as to a component that a vector can have. And a vector can either have I hat, j hat, or k hat components, and that's it. Okay, we could have all 3, but we can separate those components into I, j, k. And what we want to do is we want to see what happens if we take a cross product between different combinations of these components, because that's really what we're doing up here. Every case that we have up here, 1 through 6, is just a different combination of a vector component. And of the 3 components here, let's see, there would be 9 different possible combinations that we could try. There would be the I hats crossed with every combination. There would be the J hats crossed with every combination. And there would be the K hats crossed with every combination. And K hat cross K hat. Okay. Well, why do we need all 9 of these? Because we want to see how they evaluate. And we see that there are similar combinations here, like I cross J, J cross I. Are those going to be the same? Are they going to be different? Can we just say that they're going to be the same right now? Well, no, we don't want to jump to that conclusion yet, because again, we want to see what happens when we evaluate these things. So, first evaluation, I cross I. You have 2 vectors that are in the x direction. So when you go to evaluate a cross product, remember that there is a sign relationship waiting to be evaluated. And when it comes to 2 vectors that have components in the I hat direction, there's only 2 possibilities. Either these are running parallel to each other, in which case the angle would be 0 degrees, or they're running anti-parallel to each other, in which case the angle is 180 degrees. Either case is going to result in a 0 for the cross product. So this combination right here is a 0. It does not give us anything. Likewise, we should expect the same thing from the J cross J and the K cross K. The only possible angles that we get out of those combinations are 0 and 180. Both of those are going to evaluate to 0 once we plug them into that sign relationship. So all those are zeros. But everything else, every other combination, has some kind of 90-degree relationship between these components. Just like all of these had. So we need to take a moment and see what's going to happen if we take cross products of vectors that are pointing in different directions. And we'll start with the I cross J hat combination. I'll erase this and make some room. I cross J hat. When I evaluate this, I take the magnitude of each vector times the sine of the angle between them. Sine of the angle between them is 90 degrees. Sine of 90 is 1, and so I get the result of ij. But this result has to have a direction. I'm using one vector that is in the I hat. I'm using another vector that is in the J hat. Whatever this answer is, it has to have, actually I should get rid of that. Whatever this answer is, it has to have a vector direction that points perpendicular to the 2 vectors that were used to make it. Well, only a vector that points in the K hat direction is going to meet that requirement, but it could be plus or minus K. Either of those would be 90 degrees with respect to I and J. So which one is it? Again, we're kind of at that 50-50 choice of what's going to happen. Is it a plus or a minus K hat? That's the question. Here's how we know. If you can follow the alphabet, then you will know what the sign notation on your cross product evaluation needs to be. For our cross product multiplication, we only have 3 letters to consider, I, J, and K. And I, J, K, that is alphabetical in the ordering. So first we have I, then comes J, then comes K, and that's it. If you follow the alphabet when you are evaluating your cross product, then the outcome will be positive because you're going in the right direction. I cross J results in positive K. Why? Because you are following the alphabet with your cross product. The first vector in your cross product is I hat. The second vector in your cross product is J hat. That is an alphabetical order. As such, the result is a positive K hat. Well, there was another I hat, J hat combination right here, but it was J cross I. So what happens if we take J cross I? Is that alphabetical? Are you going in alphabetical order? And the answer is no. You start with J, then you have I. That's backwards. In that case, you are going against the alphabet. And if you're going backwards, well, I guess we could say that's kind of a negative thing, but that means that the result is going to be a negative K hat. Let's try another combination. Let's try J hat cross K hat. That was one of the combinations that we had up here. That's right here. J hat cross K hat. What's that going to result in? Well, is this an alphabetical ordering? Does J come before K? And the answer is yes. And so our outcome, which could only be plus or minus I, since we are following the alphabet here, is a positive I hat. And then if we switch around the order, well, that's against the alphabet. That's a negative I hat for the outcome. Okay, we have 2 more combinations to consider. I hat cross K hat and K hat cross I hat. Now, this one can be a little confusing for some people. We know that the only possibilities are going to be positive or negative J hat. But let's just go for it. Let's look at the first combo. I hat cross K hat. You look at that and you ask yourself, is this alphabetical? Does I come before K? Technically, yes, but you skipped a letter. It should be I, then J, then K. What we want to do whenever we evaluate these cross products is ask ourselves, what's the quickest way of getting from that first letter to the second letter? In the case of I cross J, well, I start at I and I just go directly to J. But in the case of I cross K, what's the quickest way of getting from I to K? And here's where we need to sing the alphabet song. Okay, we won't go through the whole alphabet song because our alphabet is only 3 letters long. I, J, K, that's it. That's the song. But what do you do at the end of the song? What's the last line of the song? And the last line is, next time, won't you sing with me? So you have to start over. I, J, K, then we start over. I, J, K, start over. I, J, K, start over. So when you get to K, technically the next letter in line after K is going to be I. And so if we ask again, what is the quickest way of getting from I to K? Well, that would be to go backwards against the alphabet. You know, it's kind of a weird explanation, but it actually makes sense once we apply it to this situation, because we now know that by going against the alphabet, we get a negative outcome. And so I cross K is going to equal negative J. So what's K cross I? Well, for K cross I, what's the quickest way of getting from K to I? And if you think it's to go this way, well, you've got something in between there. J is in the way, but if we just start the song over, well, that's the quickest way of getting from K to I. And we are following the alphabet song. Next time, won't you sing with me? We start over. And so this outcome is going to be a positive J. And this is everything that we need to know to evaluate the cross product of all of these vector combinations up here. Every one of these combinations, combinations 1 through 6, are going to utilize this cross product expression. We need to take the direction that our velocity vector is pointing. We have to cross it with the direction that the magnetic field vector is pointing. And the result, in addition to having the scalar value of the charge, the result of that vector cross product is going to be the direction of our force vector. So how does all of this stuff fit together? Well, we're gonna take the basic definition of the right-hand rule. Now, previously we said that this is what we were going to use for our XY axes, but now we're going to redefine our fingers as the individual vectors in our cross product. The first vector in your cross product. So when I say the first vector in your cross product, let's take E cross F equals G. The first vector in your cross product is the first vector in the evaluation process. The second vector in your cross product is the second vector in the evaluation product. And then we have what we call the resultant vector. So this is what we get as the result of combining those vectors together. The first vector in your cross product will be your index finger. The second vector in your cross product will be your middle finger. The resultant vector that you produce from your cross product will be your thumb. All right, so now is where you get some practice using this right-hand rule. We already know that the first two case scenarios are going to result in a 0, and that's because the sign relationship between those vectors was either 0 or 180. But all the other combinations have a 90-degree relationship, so all that's left for us to do is evaluate the direction that our force needs to point. So here we go. For case 3, now for all of these, the first vector in our cross product is the velocity vector. So the velocity vector is going to be where we point our index finger. So in every case, we're going to point our index finger to the right. The second vector in our cross product is the middle finger. And so as we keep our index finger pointing to the right, and you should be doing this as we're watching the video, so point your index finger to the right, we now have to rotate our wrist in order to point our middle finger in the appropriate direction of where the magnetic field needs to point. All the while, we need to keep our index finger and our thumb at 90 degrees with respect to each other, because that's how each of these combinations has been drawn out. Once we have our index finger pointing in the direction of the velocity, and once we have our middle finger pointing in the appropriate direction for the magnetic field in each case scenario, then we pop our thumb up, and our thumb needs to be at a right angle with respect to our middle finger and index finger. So our thumb will be the direction of the resulting force. And if you go through all of these examples, you will see that the direction that the resulting force points in follows this method. So for case 3, I have my velocity pointing to the right. I have my field pointing up. The only direction that my thumb can point without me breaking one of my fingers is out of the page towards me. So that one checks out. If we keep our index finger pointing to the right, but we rotate our wrist so that the magnetic field points down, well, now the only direction that the magnetic force can point is into the page. So that works. If we keep our index finger pointing to the right and we have our middle finger point into the page, our thumb pops up and points upwards. So that one works. And then we point our index finger to the right, and careful with rotating your wrist. You don't want to strain yourself or break anything. But then we need our middle finger to point out of the page, and our resulting force ends up pointing down. So the right hand rule works very well when it comes to evaluating the direction that a resulting force has to point. But the IJK process works to help us in evaluating whether that final vector component needs to be positive or negative. And we're actually going to use this method as an alternative means of evaluating a cross product. The first way that we have of evaluating a cross product, let me step back here. We had used vectors E and F equals vector G. Our first means of evaluating the cross product only provides us with the magnitude of vector G. If we know the directions that vector E and vector F are pointing, then we can extrapolate the direction that vector G needs to point. But right now, the only thing that this gives us is a magnitude. If you remember evaluating dot products, there was a similar situation where we may not have known what the angle between these two vectors is. Remember, it's only the resultant vector that has to be perpendicular to the original two. We don't necessarily have to have the original two vectors perpendicular to each other. That was the nice thing about this example that we've gone through, is that cases 3, 4, and 5 all had 90-degree relationships, but cases 1 and 2 did not. They were parallel or anti-parallel. And we can have angles anywhere between 0 and 360 for any kind of angle pairing. And so how do we take a combination of vector components and evaluate the cross product using those components? Well, everything has already been done for us. We already know how components are going to combine in a given situation. So what I'm going to do is I'm going to write out the cross product, keeping in mind that there's the Q value waiting out there. But both of these vectors could have X, Y, and Z components associated with them. If I want to take the cross product of these two vectors, then I should consider taking the individual cross products of every possible pairing. And that means another 9 combinations, like we had up here. But we've already done the work for this. We already know what all of these outcomes should be. Every combination here is some combination of 0, 90, or 180 degrees. Everything down that diagonal is going to result in a 0. Everything else will result in some kind of vector outcome. So let's see what we get. We will have Vx crossed with Bx. We'll have Vx crossed with By. We'll have Vx crossed with Bz. We'll have Vy crossed with Bx. Vy crossed with By. Vy crossed with Bz. And lastly, Vz crossed with Bx. Vz crossed with By. Vz crossed with Bz. Now, right here, we know right away that these three are not going to produce anything, because each of these has the same letters in their dot product. So I hat represents the x direction. I have 2 vector components from the x direction. The only possibility is that we have a 0 or a 180, and so no outcome from that one. Likewise, there's no outcome from a j hat, and there's nothing from a k hat. Vx cross By, I have an I hat cross j hat. Vx Bz, I have I hat cross k hat. Here we have j hat cross I hat. Here we have j hat cross k hat. Here I have k hat cross I hat. Here I have k hat cross j hat. And I know what all of these combinations are going to result in. I know that I hat j hat results in a positive k hat. I know that I hat k hat results in a negative j hat. I know that j hat I hat results in a negative k hat. I know that j hat k hat results in a positive I hat. I know that k hat I hat results in a negative, positive j hat. And k hat j hat results in a negative I hat. So you can go back up top here and review those outcomes. But again, I'm just using the alphabetic order approach. But if you notice, you get 2 of each kind of outcome. We get 2 k hats. We get 2 j hats. And we get 2 I hats. We have a plus and a minus for each, but that means that we can combine everything into a single general expression that will tell us how our final cross product is going to evaluate. So I'm going to put everything together now into a single statement, and you'll see why I'm putting together the things in the way that I am. I'll start with the I hats. I have my 2 I hat terms that I've circled in the purple highlight here. One of them is positive, one of them is negative. And after we take care of the cross product portion, remember that the cross product is hiding a sine theta. That sine theta is sine of 90, which is 1. So the only thing that's going to be left is the product of these component values. And I'll start with the values that produce the positive I outcome. And then I'll subtract the values that come from the negative I outcome. Why am I subtracting? Well, because this indicates that the result would be pointing in the negative I hat direction. Then we'll put together the j hats. There's 2 j hats, and those have been circled in the green highlight here. Again, there's a positive and there's a negative, and I will combine them accordingly. I'll start with the positive. I'll subtract the negative. Oops, sorry, that's the wrong one. It should be Vx BZ. And lastly, we have the k hats, which are highlighted in the blue there. Again, one is positive, one is negative. We'll write those out accordingly. So what does all this mean? Well, I have a whole bunch of stuff here that comes together to make an I hat term. I have a bunch of stuff here that comes together to make a j hat term, and a bunch of stuff here that comes together to make a k hat term. Well, these are I, j, k components of a resultant vector. That resultant vector is the magnetic force vector. The only thing that we're missing is that Q value. Remember, way up at the top here, when we go to evaluate our cross product for magnetic force, after we're done taking the cross product of our velocity and our field vector, we have to multiply by the value of our charge. But now we have, let's see if I use the appropriate colors here. Now I have the x component of my magnetic force. I have the y component of my magnetic force. So if I carry through the value of the charge onto this term, I'll have the y component of the magnetic force. And then I think that one, yep, that one was blue. And so I incorporate the charge with this last combination, and I get the z component of the magnetic field. So this whole expression here, everything has been generalized, but that's to our benefit, because now we can take any two vectors of velocity and magnetic field along with any charge value, and we can evaluate the components of the force vector. Now, some of your problems may only involve two-dimensional velocities and magnetic field vectors. If that's the case, there are going to be a lot of terms in this expression that drop out, because with two-dimensional systems, one of your vector directions is going to be 0, and so we're going to see this system collapse down to something very manageable if we just have a two-dimensional system. But it's important that we see what the full three-dimensional situation could look like, and then how we would evaluate. But keep in mind, between the two methods of evaluating your magnetic force vector, if all you're trying to do is figure out the magnitude of your force vector, well, would you rather use this component approach, or would you rather use the more basic evaluation? And again, this assumes that you know the angle between the two vectors. If I have components of these two vectors, there's really no way of knowing exactly what the angle is between these two vectors unless maybe we've gone through some of the Calculus 3 methods that you can use to measure angles between 3D vectors. But otherwise, these are the two options that we have. So please use this method if you can. Only use this method up here if you have components given in terms of your vectors. All right, I'm going to call that quits for this video. So we've seen the definition of magnetic field. It's going to be the ratio of our magnetic force to the electric charge and how fast it's moving through a given system. But we've now seen that evaluating that magnetic force is a bit more complex because of the fact that we're producing that force from two different vectors. And that vector multiplication has to be the cross product, not the dot product, the cross product. And that cross product takes a bit more effort to evaluate. But there's a lot of information here. The big one that I want you to focus on is in using the right hand rule to evaluate the directions that these forces need to be pointing. And if you note here, I did not actually establish XYZ directions. If we needed to, we could establish a direction for all of these velocity vectors. We could then correspondingly establish directions for the magnetic fields and the force vectors, but really all I needed to know was where they were pointing in relation to each other, and the right hand rule takes care of everything else. I don't actually have to know the IJK relationships. The only time that this comes into play is if I have to use the component method of evaluating, which again, hopefully we see a minimum of those types of examples. So in the next not the next chapter, but in the next video, we're going to take a look at a little bit of the history as to how these magnetic fields and magnetic forces were mapped out in relationship to the electric charges and the electric fields in the system. So we'll see you back for part 2.